This is a video showing a multitasking Teleo-Reactive agent interacting with a simulated environment with 5 resources. You have to imagine that there's a camera in the environment that can read these numbers on the blocks and tell where the blocks are. That 14 is directly on the table, and if 4 is moved on top of it, that 4 is on top of the of 14. The arms are resources that are going to be used by the agent to build 4 towers of 4 blocks each, 2 on this table and 2 on that table. There's a constraint on the use of the arms, that this arm can only reach that table and the middle table, and this arm can only reach this table and the middle table. So the middle table is a shared table, but the towers are going to be built on the 2 end tables. As we run this Python simulation, you'll see messages. You'll see that percepts are being sent across to the agent that's running in here. And when I launch the agent with this go prolog command, it's implemented in a multi-threaded qprolog, it will launch actually 5 threads. One is a percept handling thread that will handle the percepts and update its belief store, and the other one will be the 4 task threads. All the task threads will be looking at the same belief store. Let's start it off, and then I'll give you more information when it starts running. Alright, so these now are the 4 tasks that are underneath the tables where the towers have got to be built. So this task 1 is building the table, the tower that starts at 2, 15 on top, 3 on top, and so on. Okay, and it's actually that task is about to put 15 on top of 2. The color coding is used to indicate which task has got control or has acquired certain resources at a given time. So this is telling us that task 2 is using this arm, this table, and the shared table as resources. Why does it need the shared table? Well, because it needed to pick up a block on the shared table and move it across to this table. The shared table is a crucial resource that can there's only one task that can have access to the shared table at any one time, and that stops the clashing between the 2 arms. We can never have 2 arms going to pick up from the shared table at the same time. Here we've got some parallel use of the other arm, and task 3, color-coded blue, is using that arm, and it's just using this table because it was transferring 1 block from one position to the table on top of, let's see, it's putting on top of 13 on top of 16. So it's about to put it on top of there. Let's run it a bit more. So this is pulling up, so task 4 was pulling something from the shared table. This blue picked up that arm and used it to move a block to the middle table because it needs to pick it up later. So in a little while we'll see task 3 coming in. I think it was 5 that was transferred over. No, it must have been 14. 14 was transferred over. Alright, well, while the tasks are constructing these towers, as with all Teleo-Reactive programs, we can assist or we can hinder. We can help or hinder. They're nearly completed, but let's do a little bit of hindering. So task 2 at some point is going to have to pick up 10 from the shared table, and at the moment task 4 is going to, what's it going to do now? Looks like it's poised over 10. Why is it poised over 10? Has it just dropped 10? Maybe it's just dropped 10. So I've actually put it back onto there, and in fact we should be picking that up at some point. Okay, so this task has used that arm to put it on the shared table, and now it's using the other arm to pick it up from the shared table and move it across. Now, all Teleo-Reactive programs are achieve and maintain for their goals. A goal is usually the guard of the first rule of the initial procedure. So if we disturb these towers once built, the task will try to reconstruct them. So they're running inside this agent, and they're sort of chafing at the bit, monitoring this belief store here. So the beliefs tell us the configuration of all the blocks. So for example, it tells us that 2 is on table 1, which it is, directly on top of table 1, and somewhere it should tell us that 15 is on 2. There's the fact that tells us that 15 is on 2. So let me do some disturbance of these towers. I'll take the bottom block from here, move it over there, top block from there, block from there, and one from here. Now, probably task 1 will kick in to try to get hold of 2, because that's the base of its tower. It needs to put it on the table so it can start reconstructing its tower. And to do that, it will have to take all these blocks that are on top of 2 off and put them on some table. Which table is it going to use? Well, one advantage of actually running all the tasks inside one agent is the agent can keep track of what the other tower building tasks are. And when it's unpiling these blocks, it can check if 9 is needed by some other task, and indeed 9 is needed by a task 3 that's building its tower on that table. So in that case, as task 1 is unpiling 9, it will leave it on the shared table. It will be using this arm, and it can't actually reach over to this other table, so it will leave it on the middle table, the shared table. When it's unpiling 5, however, since this is a block that it will need later, instead of putting it down on this shared table, it will transfer it over to this table, table 1. When it's unpiling 10, it will similarly put it on table 1 because that's needed by another task, task 2, that's building its tower on table 1. So that's cooperative unpiling. Now, why do we want to do that? Well, the shared table is a bottleneck. When there's only one of them, and when one task is waiting, building on this table for the shared table, the other task can't do anything because it can't access that arm until that arm has got the shared table. Similarly, if the first task waiting to make a move on this table onto the shared table, this arm wouldn't be in use. So the more times tasks have to access the shared table, the less opportunities we have for parallel use of the arms. So if we can minimize the use of the shared table, we'll maximize the use of the arms. Let's see if that works. Okay, 9 is being put on the shared table. 5 is being transferred for later use by task 1. 10 is being moved over for later use by task 2. And 2 is being put on as the base. Now, task 3 is kicked in to pick up the tower, the block that was left on that tower for it. Okay, let's see if we can help or hinder this task 1. That's now constructing its tower. It's already got 15 on. The next thing it's going to do is to put 3 on. So it's moving over to put 3 on. Let it move a little bit further. And then what I'm going to do, I'm going to thwart it. See if it recovers. Yep, it's gone back to take 5 off, and then gone to take 3 off. Let's thwart it again. It should now put 3 down and pick up 15. Alright, I'm going to do a slightly more complicated bit of thwarting this time. Incidentally, every time I move a block here, what happens is the simulation stops while I move blocks around using the mouse, and it stops sending any percepts over to the agent. So the agent is sitting there waiting for some percepts to arrive to update its belief store. In fact, if we look back on the log, we should see where we had, that says there was only one running task. We should have had, at some point there'll be things telling us that we have 2 running tasks. We've got a log here saying which were the running tasks, which were the waiting tasks, and so on. Actually, I can't see one where it says 2, but there will be in that log occasions when there were 2 tasks running, and that's when we saw the parallel use of the arms. Right, as this arm now has task 1 kicks in to use this arm to pick up 5, I'm going to try and fool it a little bit. Alright, so it's coming down to pick up 5. I'm actually going to flip those blocks around. So it should actually want to go back. Yes, it is. Some more hindrance. Oh, it's not going to let me do that. This is the visualization that's not letting me do it. Now it can help. Right, so final demonstration, I'll move 2 blocks way over, and then you'll see this use of both arms by the given tasks to actually transfer via the middle by the shared table. So at some point you'll see this arm coloured blue, saying that task 3 has acquired it to move to the shared table. And you'll also see at some point this arm coloured orange when it's actually going to transfer 10 over to the shared table, and you'll see that arm also coloured red when it's transferring 5 over to the shared table. Okay, that's the 5 going over. Now it's orange, so that's the 10 going over. Now blue, 14 going over for task 3. And now this one is actually picking up its block to move over. That was task 1 picking up its block. It's task 2 picking up its block. Now we have to, this task 4 will have to, oh no, it was task 3 that was short of, Alright, well that's it. That's a multitasking Teleo-Reactive agent running inside here 5 threads altogether, using elaboration of Nielsen's block tower building program, which controlled just one arm building one tower. And the tasks were executed without interfering with one another, without the arms clashing, and robustly and opportunistically.